So I'm going with the hacker nickname Neutrino, or A Neutrino, since I was, 11 years old, and the kids were laughing at school about me that I know what Neutrino is, yes. So this is why I chose this nickname at the time. And I am very lucky to work my almost entire life with Linux, and people pay me for that, which is great, and to develop open source products for almost entire life. And today, I would like to talk about these open source products which exist in the world, and not only open source, some of them are closed, which are based on the architecture which Google in 2003, with their publication, they released publication about GoogleFS, and a little bit, we have this expression in Poland, like mushrooms after the rain in the forest. They start popping up the distributed file systems which implemented the architecture which Google was so kind to publish to the world. However, in the current days, this technology requires to be improved. However, we should never forget that we are standing on the arms of the giants. So even these improvements, which we'll be talking today about, we need to remember they were only possible because some generations before us were able to make these improvements, make the basis, foundation for everything. And I'm talking about this because this presentation is humbling for some of the existing distributed file system solutions, including our own file system, which I will be actively and constructively criticizing why is bad and what we need to do to make it better, what we are doing to make it better. So I already talked about this introduction, right? What we'll be doing. So the people who are interested to see at least a little bit of code, we will be. This is on the end developer conference, and I am expecting your help to tell why it's maybe not the good idea, this what we are doing, before we actually make a final implementation. So on the end, we'll have some talking about interfaces which are being created, which is a hands-on on the code, but I would like to do some introduction and bring everything on with what exists currently. And this slide knows everybody. It's the funny part is that when the first time in my life I was talking about storage, it was, let's say, around here. This slide at the time was looking exactly the same. Yes, just the shape was exactly the same. It was just here, right? And it was, so it is never changing. This is like a tautology in the storage world. The data are growing, and they are growing not in linear way. They are going faster than linearly the need for the data storage. And the critical bottleneck which we are facing is the fact in the distributed file system particularly that the metadata needs to be processed, especially if you would like to have a shared namespace. We would like to have a place when everybody who is using our file system can see the same state of the file system. And the challenge and the critical bottleneck which exists is not actually the bandwidth about this, how fast we can get the data. We can, EOS in CERN 2 years ago announced that they are making the 1 terabyte per second transfers, and this is normal for them, right? So it's not this. It's not about that. It is about, let's call it metadata operations. And we could, to simplify it, call it IOPSs if you want to. But it is not only IOPSs. Is this what is allowing this meta information to be consistent as we expect from the parallel distributed file system, which is POSIX compliant. And On this slide, maybe it's not visible, but it is just a snippet of a very small cluster when we have literally millions of these meta operations happening all the time. Some of them are very kind of useless, like lookups, right? And they are very often dominating. But nevertheless, that's exactly what is the bottleneck currently, which we are facing the most. So the goal is to have a low latency solution, which will allow to access this metadata in the distributed and consistent fashion. And basically, this is something which is required by the current standard, which the exabyte is a new standard in the industry. No, but telling that, oh, we are petabyte file system distributed is not fancy anymore. We are in the definitely exabyte scale distributed file systems universe. So, as I said, there is some foundation which was created in 2003. And this presentation will now talk about few file systems which are based on this foundation, which was generated in 2003 by Google. What's important to note is that this original approach of Google it was not POSIX file system. It was file system, though, which was optimized for very specific operations with the very big blocks, which were 64 megabytes at the time, which is called chunks, and with single metadata server, which was still extremely revolutionary because all of the metadata could be kept in memory, in RAM, and with relatively fast Ethernet speed networks delivered to the storage. This system already have replication built. It was not erasure coding at the time. It was just simple replication. Let's call it mirroring fashion when you could make multiple replicas. And the consistency of this model was already a little bit relaxed. There was not like this what POSIX really requires us to do. There was, as I said, Google file system was originally not POSIX compliant. But the architecture made that there was popping these other file systems across the world, and I just have few of them here. This is a snippet just to show which are compatible with this technology, with this approach. And each of them, which is here, is still being used by the academia, by the industry, and by many enterprises. However, each of them faced the challenge to improve this original design flow when the single metadata server introduced was making things not as fast and flexible as we would like to. So I am currently working on the file system called SaunaFS, and this presentation will be mostly on it to give you an example what are the challenges, but we'll be referring to the other file systems. And the architecture which you see on this picture is centralized master server with a shadow. Maybe I will be showing a little bit here. Centralized, I don't know if you can see this, master server with some redundancy for the metadata servers, and very well scalable chunk servers, which we have here, and some clients which can connect through to the storage architecture. And the chunk servers particularly, they can store the data in erasure coding or replication fashion. And SaunaFS particularly is not only POSIX compliant, like for instance BGFS and the Lustre, which are there, but also additionally, we 2 years ago decided to implement support for host-managed SMR drives, because we would like very much that the regular institutions, people are using the highest density drives in the market, not only hyperscalers. So this is we try to contribute into this part of the world. And the fact that there is a single master server, metadata server, doesn't mean that there is no high availability. There is high availability, there is continuity on the metadata service and the entire file system. It's just that it's not as smooth as we would like to have it, which we will talk in a moment. So the example installation of the SaunaFS looks like that. So there's a JBot and server, JBot and server, JBot and server, and some networking. Actually, in practice, we recommend that all JBots are on the bottom and the servers are on top, but just to show the block on the schema, we just presented it here like that. And these JBots are 101 drives JBots, so they are beefy machines. And this one rack system has a capacity of 28 petabytes of space with the current host managed SMR Hammer drives, which are available on the market already for hyperscalers. Yes, but it is changing. Everybody will have access to them very soon. So what are the limitations of this technology? So the problem is that, okay, so we have everything in memory in this red part, which you see on the picture in the master server. And we have active master files, which are shadows, they are gray. And they are very fast promoted. So let's say that the master server fails because something bad happened. So the files which are being, by clients performing I/O operations, they need to have a continuity. So our current system, like many other systems of this way, very fast, within the few milliseconds, is able to switch to another master server, which basically has the same state of the memory, RAM, as this master server. So there is high availability, but there is no really balancing of the metadata in this approach. Another minus of our architecture in SaunaFS, which we have, is the fact that we would like to consistently dump all of the metadata and persist them. So normally, we have journaling or changelog, and any I/O operation which is happening is being persisted into this journal. However, journal is only recording the delta, only the changes, what happened. So from time to time, we dump the entire memory, let's say 1 terabyte of RAM, and we dump it into the single file, which is the status of this memory of the metadata server. And in order to do it consistent, we are forking the process on the master server. So the entire system can continue during the dump, and it is not destroying our consistency of the POSIX file system during the dumping the metadata. So this was good for many, even decades, I would say, right? However, now it's not good enough. And another problem which we have here is that scalability. So scalability from the point of view of the limit of how much memory really we can have. Like in CERN, for instance, they have this EOS file system, and the first metadata servers which they were doing, there was in memory and only single of them, right? So they transform and they did something with these metadata servers in order to not to have this in memory. Exactly the same problems as the original Google file system we were facing in our solution. So what is the real problem regarding this metadata? So the problem is availability, yes. So even if I said we have few milliseconds to switch, okay, that's true, but at the same time, there are some obstacles during this switching, which are making, first of all, the entire storage system to be in the I/O state, I/O wait state. Even if this is milliseconds, it still may be a problem for some of the operations. And there is our solution, our implementation of this file system is not scalable. We cannot, for instance, balance the traffic from the shadows easily in this architecture. And of course, the capacity itself is a problem. even if currently you have CXL memory, you can insert to the server and make maybe, I don't know, who knows, maybe 16 terabytes memory servers. This is still not a solution for this kind of the file system. So our objective was to eliminate these old steps, and we would like to talk right now about this, how we decided to do it. Okay, so there are some related works which we analyze before we choose our path. So we are very closely look at the SaunaFS. And SaunaFS, I wanted to say, is not a clone of the GoogleFS. It is a new approach. It's a different way of handling from the very beginning when they designed the CEF and SaunaFS. However, we put it here because it would be a mistake not to look at the SaunaFS as an industry standard currently in the storage for many applications. And so SaunaFS is using the approach of sharding, partitioning, and hashing, and together with the solutions like Lustre or HDFS. HDFS is like a Hadoop file system, and here federated version. So there's this approach, which is called sharding, partitioning, and basically hashing. Another approach, which was chosen by the clones of the GoogleFS, like BGFS or also Lustre, please notice Lustre is in two places here, right? So is to use the local file system. So if you think about this, any local file system you are using already, let's say it is XFS, right? It is basically it's having already scalable up to billions files, local, very fast. Let's maybe not call it database, but the storage, metadata storage, which is there. Yes, and it doesn't matter if this is B3 implementation or if this is another way. It's very efficient, it's very fast. It allows to deliver really millions of I/O operations per second. The problem is that the local file systems are working only on the local mediums. So you are limited with this capacity, how much you can put in one server. If you can put in one server, let's say 102 drives, that's it, that's your limit. And we are talking about this, how to build storage with 100,000 hard drives, not only 100 of drives or 500 drives only. So these local file systems like ZFS or X4 or XFS, which are there, even NTFS, they are very fast in this local metadata operation. So looks like BGFS people and also people from Lustre, they just took a look and say, so let's remove this in-memory metadata and let's locally create local file system which will mimic, in some extent, I will be talking about this, how it works, mimic this all metadata information in the local file system. So even if you have multiple metadata master servers or whatever it's called, metadata servers, MDSs, they will, instead of in RAM, they will have the same attributes, which has a file, let's say file is called foo, and it has attribute owned by user bar. This attribute will be created the same file on the local file system, and it's there, and it's super fast already. So we don't need to have some dedicated database or in-memory data structures. We just repeat everything what is happening in big file system into the local file system. We just don't put data there, only metadata in the local file system. And the real data are going to be redirected and distributed across the object storage servers. So this is like, let's call it approach how to scale metadata with the local file system boosting. Very effective, and it's working very well for both of these file systems currently. If you are lucky to use them, you should know. And of course, there are some other approaches which are using databases for storing the metadata. So the metadata, instead, again, being kept in memory, in RAM, they're being kept in some database. And this approach is chosen by many. One of them is pretty fresh in the game, and it's called FreeFS. Who knows about FreeFS? From DeepSeek? Yes, so DeepSeek published FreeFS. Unfortunately, very little quantity of commits, but it's there, it's open source. And so those people decided to store all of this metadata in the distributed database systems. So just to a little bit show you how is it looking in all of the systems in a little bit more details. So the CEF is having very interesting approach, very scalable, which is not only keeping the metadata of the particular directory in a very dedicated MDS server, but actually they can do it dynamically. They can dynamically in CEF detect that maybe the quantity of the I/O operations or metadata operations is, my time is finishing? How much time I have? 23 minutes, okay, so it's fine. So CEF is doing it in dynamic way that administrators don't need to really spend too much time on this where the metadata will be balanced. And they have very interesting algorithms about this, how to do it. On the other hand, the Lustre choose the approach when it's interface which is called data management unit approach, which is kind of abstraction layer on top of the ZFS metadata operations only. So they use ZFS or ZFS, and they make sure that all the metadata informations are already taking all the advantages of the ZFS system, which is coming with, for instance, write-Z feature for protecting the data, taking advantages of the ARC system in the ZFS, which can cache a lot of the operations in RAM. So just what they needed to do in Lustre, they needed to implement this interface that from now, all the POSIX attributes and all the metadata information, let's say, extended attributes, so on, they're going to be stored inside of ZFS, which is kind of castrated, that it does not have any hard drives. This is ZFS without hard drives, right? Because the hard drives are through the network distributed and delivered by the Lustre object storage servers. So this is a little bit like how to make ZFS to become the distributed file system. So the Lustre found a way how to do it, yes, and created this interface. And very similar approach, in the moment I was talking about similar approach. So this is like another approach when the HDFS decided to do it this way, that they have a name nodes per directory, but the minus of this solution is that it's manual. So administrator of the storage system needs to tell, okay, this directory is going to be on this name server, this subdirectory 3, sub3 is going to be on this server. So it requires some manual management about this, what kind of metadata are going to be located in what place. And by the way, all of these solutions which I am talking right now have a big challenge. What happens when somebody is moving a huge sub3 directory into another directory, and which is owned by different metadata server handling it, right? So how to do it effectively, how to do it consistently, atomically, challenges which all POSIX system is giving here. And another example, BGFS. BGFS can work on ZFS, but not only, also on XFS. And I was lucky to talk to one of engineers of BGFS on CloudFest, I think, and she told me that at the time, it was 1 year ago, they are using this ext4 file system, which can be mirrored to another server. So they have a redundancy. When one of these metadata servers disappears, the other one has the same state of this, let's call it, I would call it castrated ext4 file system. Castrated because without, I don't know if this is the correct word, maybe I should not. So please, but I'm from Poland, and castrated means that something was cut, yes? And that's it. So maybe I should not use this term. I just start realizing it. So sorry for that. But at least I wake you up. So let's call it limited file systems without the object version. So all of this related work, we have been analyzing, and we were thinking which approach is the best, what to choose. And there are advantages of having already a lot of tools which exist. Like, for instance, ZFS already has existing fantastic tooling for metadata operation acceleration, so why not to use it in maybe SaunaFS also? And this was the part of our research. And also, something which we noticed in this approaches by the other file system, distributed file systems, was that MDSs, because of this, let's call it sharding or this, making them horizontal, become much more lightweight. There are, because the original approach of Google was such tempting to put everything on the metadata server, like everything. If there's one metadata server, why not to have the duplication on the same server? Why not to do scrubbing of the data on the metadata server? So suddenly each of these file systems, before they did this, let's call it, and find the word, trimming, before the trimming, they were putting so many services in this already overloaded metadata server, right? So now, what is interesting, after our research, we noticed that they are not doing it anymore. Now MDS is serving only metadata and nothing else, and all these services, because of the vertical scalability, could be moved as external services outside, which is only bringing another plus for our huge exascale storage file systems. So one of the things which also this new approach is doing is that it's making all of this heavy lifting, the metadata servers, which are hard problems. So as long as these hard problems are like transactions, we need to have transactions. We need to have a consistency, of course. We need to have a replication for high availability of the metadata service, right? And of course, we would like to have a sharding. So all of this was part of our research and how these other file systems tackle this. So our solution was created, okay, so we'll go with the ACID database, okay? So we are currently implementing it. This presentation is already old because we needed to send it much sooner. But we are currently implementing this approach very similar to FreeFS from the DeepSeek company, which created FreeFS. And why we choose the ACID database? Well, this is just example on the screen. You can see on the screen the motivation, what we are having for free because of this database. And also here, in this orange side, it's not red anymore. You just see that this layer of the MDSs which we have is only taking care to maybe cache, but in a very nice, consistent way. This is what the distributed file system is doing for us. And distributed file system is managing all the replication and making sure that the transactions are being processed. Plus, we can have external services which don't need to real-time state of the metadata, but are extremely crucial for any huge storage system, like scrubbing the data, for instance, regularly, right? So we also have, of course, the single source of trust right now. So this database, we decided to go with the FoundationDB, by the way, database, and I will show a few implementation details. We don't have any more problems with the downtime of the metadata server to think how to synchronize it, even if we are proud that we can do it in the milliseconds level, which is, some other solutions with CoroSyncs are taking seconds to transfer. We think, oh, we are doing it in milliseconds. Now we actually don't have this problem. And another thing which I wrote here is no forking needed. So this forking, which I told you before, I don't know if you remember, I was telling that from time to time, our metadata server needs to fork itself in order to have a consistent metadata dump into the file. So the problem is that when you have 1 terabyte of RAM allocated and you are forking, Of course, it is not taking 1 terabyte of RAM because Linux for a very long time has copy on write during the forking. However, because of these other assisted services like scrubbing and so on, it appeared that most of this forking-based metadata dumping, which can take, let's say, 8 minutes, during this 8 minutes time, almost entire memory is actually a little bit modified, touched, and we need 2 terabytes of RAM. So for 8 minutes on, we need this 2 terabytes of RAM. So we don't have this problem anymore with this distributed model, of course. And another benefit is that our changelog, the journal, which I said, so the journal originally was just a file where we were appending every operation, like somebody changed attribute, somebody changed the name, somebody moved the directory, so on, right? This was like a changelog. This changelog right now also is being inserted into the local, on the every MDS, local every MDS database, which allow us to start applying on the changelog a lot of interesting tools, which, in the future, some people would like to have anomaly detection on the file system, which is assisted with, let's call it LLMs or AI, if you will. Yes, but now the fact that we have this almost infinite quantity of the changelogs available for the people in the nice structured way, not just as an append log, the new opportunities are opening on the file system in this regard to analyze the metadata operation, including the archive systems, when you need to tell how often something is being used, how often it's being read, and so on. You just wanted to have this kind of tiering in your archive systems, and now we have all of that also in the separate local databases systems as a changelog kept on each of the MDSs under one clustered umbrella on the FoundationDB. So another very specific thing for our file system, the other file systems don't have it, but our file system, when the chunk server, which means the object storage is connecting, and let's say it is 100 to 36 terabyte drives. So we're talking about 3 petabytes of data. It's just appearing and it's connecting. The chunks, the objects, they need to register in our metadata servers. So this was something which was also making a problem when there was a massive electricity failures in the data center with 400 servers. And then all of them were trying now to register all of these billions of chunks inside of the metadata layer. So this was a problem which we don't have anymore also thanks to this solution. There is some price which we pay for this, which I will talk in a moment, and you will have a possibility to ask the question. So to sum up the solution is to use the distributed database with very light MDSs, however, with a lot of RAM still to allow local caching for some metadata operations, which are especially read-only, appearing in the parts of the storage which now could be detected as a read-only. And that's a massive quantity of the operations. And external services, which doesn't need to have even consistent state to perform operations without touching MDS layer. And of course, there was different databases which we're considering, which are being used by the file systems over the world. So this one is used, this one is used. There's a Hadoop file system called, what is this plant to make beer? What is the name of this plant to make beer? Hops? HopFS is using MySQL database. There is a FoundationDB also, which is key-value. I didn't see any distributed file system using NoSQL for metadata layer. Yes, if you know, please talk to me on the break, and I would like to know if there is such solution. And the FoundationDB was chosen because it's open source, it's transactional key value store, right? Exactly all of this, which is bold on the screen, as you can see, and also. The fact of the distribution means that it's also highly available. So we are not talking about just sharding and then trying to create replicas for sharding. The FoundationDB has a model which allows safely distribute this data which are stored inside of this database, and it's also very fast. It's also fast in the moment I will tell you why, because of the model of making transactions in this database. So what was the implementation details challenge which we needed to implement? By the way, we coded in C++, yes? So first of all, this is how it was. So we have this model that there is a metadata SFS file, very big one, dumped every hour on the master server, which has information about every node, every inode, every edge. Edge is information, what is my parent directory? So it's inode to parent directory. It could be multiple parents because of the hard linkings, yes? So, and what are the free means inodes which we want to reuse? Because, you know, even if you have, let's say, 2 to the power of 32 of the inodes, on the beginning we have this one, we're thinking it's a lot, but people were creating and deleting the files, so we need to reuse them. So they are being recycled. With the 64-bit nodes, it's not as needed, but anyway, historically, it was 32. Extended attributes, access control list, quotas, information, file locking, and chunk versioning and locking. Chunk is a block storage information. So all of this was stored in the original metadata server as this section. So if any of you will need to do this kind of job and transit from this, let's call it, approach of single master server to the distributed one, the way which we recommend to do it is to do it progressively, that the entire system is always working. Instead of trying to create from the scratch the new file system on the side, which now will use the database, let's say, which is going, in my opinion, to fail and is much more complex task, it's much better to make old solution which is totally working and start replacing block by block only one of the components when, for instance, the node will be already stored inside of the database, but the rest is still in the file and is still in the memory of the single metadata server. But at least this part can be already distributed, and you can reuse existing testing infrastructure for your file system to see if it's all working and if it's consistent. And you can iterate every week to have something which is better and progressively, asymptotically bringing you to this fully distributed metadata server. So I think I'm repeating myself here. Yes. This is just to also explaining that not only we store all of this data, but also in our legacy system, which we are now replacing with new one, we needed to synchronize all of this metadata with the shadows. So all of this code, this logic, was part of our metadata servers, which now, and by the way, very big elephant in the room, is this metadata server is also single-threaded. And that's because we need to fork. You know, in Linux, not only in Linux, it's not a good idea to fork when you have multi-threaded application. You can end up with a lot of memory leaks and the other extremely bad situations. So this is another architectural, let's say, minus, right? So now we don't have it anymore, and our metadata servers can be not only multi-threaded, but can be actually multiple metadata server processes on the same machine even started. So it is just talking about this fork. Okay, so from the programming point of view, what we need to focus is that there are different types of data, which now we used to have them. We used to have them in memory, and now we don't have them in memory anymore. So we have them in database. So metadata version is something which is just incremental value, right? So there is one version at the time always of the file system in the POSIX universe. It's always one, right? And there is a max inode ID, which we used to have in our solution, and this was also incremental. However, we were reusing the free inodes for recycling. Another challenge was next session ID. What is session ID? Every client which connects, every device which connects to our file system, it has the own ID. So we needed also to be sure that they are unique, right? Another thing is like metadata checksums. So our file systems was designed, SaunaFS was designed that even if you don't have ECC memory, we have a checksums of everything in the memory checked and verified all the time. Some people say, yeah, you are using a lot of CPU for that, but to be honest, not really, which it's just, we need to make this checksumming. But my point is that all of this was in our old, perfectly working, by the way, solution. So this new metadata implementation is going to be like that. And as I said, we are doing it progressively. So we still keep the old way when we keep the file, when we store all of these rows, which I mentioned. And next to it, we created FDP. On the beginning, just keep, let's say, inodes only. And the rest is dummy. The rest is not implemented yet. But because of that, we are reusing entire infrastructure with hundreds, if not thousands, of automated tests of the file system, which we already have in place. And there were interfaces created, like interface for key value engine and the interface for the transactions. So this kind of abstraction in C++, which we created, they allow us in one place now just switch between, do we want to use it in the file or we want to have it in the database, yes? Where do you want to have it? So we need to do this kind of refactoring of this code. And another controversial decision is that a lot of things which is happening in the master server, in the metadata server, it's implemented on the signals. Like in Qt, I don't know if you are familiar, in Qt there are signals. So we are also using our implementation of the signals, which is compatible, let's say, with the idea of Qt. And before anybody says that the signals are 100 times slower than the manual handling, which we could do, this 100 times slower, it's still fine because it's nanoseconds level. And please notice that this signaling is only happening on the single metadata server, which now we can have 100 of them, of these metadata servers. So okay, one single metadata server can handle currently, because of this constraint of signaling, maybe only 20 million I/O operations per second. We are fine with that because we can scale it horizontally from this moment on. Yes, and this is just an example of this signal implementation. You can see how is it looking, and this is example how easy it was to change the test framework. So we have hundreds of tests, which normally have this kind of parameters to start the storage and then execute the test case on the storage. So the storage, distributed storage, must be initiated, must be in some state, and then the test is being executed. And creating all of these tests from the scratch only because we try to create distributed metadata file system would be a pain in the neck. I trimmed this word. So this is what we needed to add to make it now compatible with the database version of our storage. The same test cases are just copied and just added extra one line. You will be using FoundationDB as a storage. And example implementation in the database itself, how does it look like? So before, the node was, integer. It was a map, yes, integer to attributes, which are another bytes of data, right? So basically, map from inode into the attributes which are existing, the POSIX attributes. Sorry, I just missed the words. And in database, we needed to do it the way that we define what is a key right now, what is the key, so it can be very fast taken from the database, and the database itself has their own mechanisms to build the indexes and accelerating the way of retrieval of the data. So this is just example. What is the key? It's exactly this, what is in the these brackets, which are looking like bigger and smaller. I don't know what is the English word for that. And another one, the edge, another key is inode of parent and inode of child, and then is a name, which could be the name of the particular file or the directory, yes? and so on. So this is the example, again, how this is implemented. And on the right side, each time when I'm switching, you see how does it look in the database, yes? So there's not really redundancy by the database created. From the point of view, the database is keeping it very nicely as integers, as a binary numbers, not as any strings or anything like that. And it's performing very fast searching of these keys and values for us. And another very interesting thing which we liked about deciding to go with the Foundation DB is that is optimistic concurrency control. So basically conflicts are solved only when they really need to. And we are file system, so we have always ability to retry. And the I/O universe is coming with this kind of support, like I will retry again. I am in the I/O wait state. So these collisions are going to be solved smoothly by the architecture which we already had, and are very nicely compatible with this optimistic concurrency control inside of the FoundationDB. So I will show the results. How does it work? Because we already implemented prototype, and we have it working in our lab. So this is the lab scenario when you can see 8 metadata servers versus 1 before, right? And because the tests were done over a month ago, we still had hard-coded splitting of the, let's call it, inodes IDs of the files to the very particular metadata server, yes? So each of them has their own range of the inodes which it is handling, yes? And all of this was started on the single server. So on the single server, we start 8 processes of MDS. And I don't know if you can see, I need to go there. The results are here. So, well, it's really not readable, but this is better showing that there's a linear, I put the red line to show that it's linear, because it doesn't look like it looks like it's like flattening, but it's not, yes? So this one is, for instance, completely in line with this. There's just, here are some overheads. So this is a 16 parallel metadata servers serving the metadata with the speed of our in-RAM metadata server currently, and this is already using external cluster DB over the network. It's not very fancy network, by the way. It is a typical regular 100 gigabit switch without any fancy features. And we managed to achieve the same, on the prototype level, the same speed of metadata operation as we had in a single threaded memory metadata server. And also the loading time of all the metadata. So, when there's a real disaster and there's really no electricity, let's say, for longer than the diesel can pull the data center, and you need to start everything again, there's this moment when all of this needs to load up and start working. In our previous solution, we have this problem that, unfortunately, it was pretty slow. It could take like 10 or 20 minutes. And now we are already on the level of doing it with this approach in parallel, 16 times faster, actually even beyond this, over 100 times faster already. So that's it, what I have for today, to be honest. I wanted to just tell you that file systems, distributed file systems, for many years were serving and giving us a great job, and all of them currently are transforming to this model when the metadata are much more horizontally scalable in order to deliver the better than ever performance in the storage. And this is our way how we decided to do it. If it's not correct, next year I will talk about this, what is the new approach which we decided to do. I'm sorry that there is no time for questions. I'm afraid, but maybe on the corridor.